Thanks, Philip. Thanks for the intro. Yeah, hi, my name is Chris, and today I'd like to talk about a tool or a suite that we developed over the last 1.5 years, basically, which is about demystifying intersecurity technologies in the firmware, and the tool is called the Converged Security Suite. Everything is open source, so that's good stuff. And yeah, first of all, I'd like to talk a little bit about what motivated us to write this kind of tool and to write this suite. Like what the problem that we had to solve there, and why did we go that way, and how did we took it, basically. I want to give you like a short background, even though like I think most of the people know what intersecurity technologies are out there, and like how BootGuard works, and how TXT works, and how CBT works, and these kind of things. I just have like a couple of slides to recap this. I'll try to go over that quite quickly. Then I'll talk a little bit about manifests. Manifests are data structures that we do care about. Then I'll talk about the Converged Security Suite, and maybe if you want to, and I still have time, I can give you a short demo. However, as I said, everything is open source and available. You can also try it out yourself if you want to. All right, let's dive into it. What was the problem, or what was actually what we had to do? So basically, my background here a little bit is I'm a firmware developer, and I'm also the head of 9-element cybersecurity, and we're in an agency, basically. And that means we're doing contract work, right? And a customer came to us because we are working quite heavily in the open source firmware world and ecosystem, and also experts on firmware security. They came to us and said, okay, we want Intel Converged BootGuard and TXT basically implemented in core boot. So that is simple from task point of view, right? To implement feature X. However, when we start looking into this, and of course we already had like a feeling about it, it's not that simple as it could be, right? There's no proper documentation about like CBT, how does it really work in like deep down. We didn't have any reference system available. You can hardly find any system that you can just buy which has Intel CBT enabled. And we are also working on interscalable systems, so that made things a little bit more complicated. So that means we didn't have any reference whatsoever available that we can compare against. All the tooling that is actually out there, that for CBT, you have to follow like a provision ritual, and you have also configure your platform, or your firmware has to configure your platform in a certain way. And all the tooling that is actually available is UFI only, right? As already said, we're working most of the time with open source firmware, meaning there is no UFI, and we actually don't want UFI for various other reasons. However, that is not a case for us. So it means provisioning, no tooling available, everything is Windows-based, everything is UFI-based, it can only pass UFI images, big problem for us. Also validation, everything is UFI-based, right? So that means, or that meant actually, bottom line for us is there was no proper way to actually audit or validate or even provision the firmware that we're going to write, and also the firmware features that we should implement. So a small recap about Intel security technology, right? Intel does release, or has already released, a couple of security technologies which do live partly in the firmware or in hardware or in the OS. And just the most prominent are like Intel TXT, also Intel Trusted Execution Technology. You got Intel BootGuard. You get both merged together as Intel Converged BootGuard and TXT. There's something like the Intel BIOS Guard, there's SKX, there's PTT, there's PFR, there's TME, and then I guess there are other three character abbreviations that there are there. So there's a lot of stuff going on, and there are a lot of different technologies, and all these technologies do need different things. Small recap about Intel TXT, right? Intel TXT sets up a trusted execution environment. It basically facilitates two trust anchors. The one is a TPM, or it needs a TPM on the platform. The other one is it's running authenticated code modules, which are basically binary blobs, and they need to be trusted. So you got two trust anchors here that you're working with. One is the ACM, the other one is the TPM. It can run in two modes: auto permission mode and also signed policy mode. I don't want to go in too deep, but auto permission is basically the platform sets itself up on the first boot, basically, and then it tries to keep the configuration it has on the first boot. Signed policy mode is you have more freedom, but it's actually harder to configure. Into BootGuard is another technology that introduced, and it does boot flow protection. BootGuard verifies the IBB that you can set, and only if the IBB has been verified correctly or is correct and is what it expected, it will actually boot the platform. There are a couple of modes it can run in. First mode obviously is disabled, so that's no use at all. It can run in a measured boot, or it can run in a verified boot, or it can run in both. It has various error handling that you can enable, like if the IBB is not correct, it can just immediately shut down. As Ian already pointed out, that might not be something that you want to have either in critical infrastructure or, for example, when you're on a hyperscaler and have like a big server fleet, you do not want, if something is wrong with your firmware, that the whole server fleet is not booting up anymore. It can shut down after a couple of seconds or minutes, or it can actually basically do nothing, and you can read it out, and then maybe have the remote attestation takes care of validating if the platform can be trusted or not. It facilitates different trust anchors, so it also uses an ACM to do the measurements. However, it doesn't use the TPM, but instead it uses the ME, and the ME has fuses in there, and the hash of the IBB basically is burned into the fuses in the ME, so basically in the source bridge of your system. The thing that we were working on, so you got background on TXT, and you get background on BootGuard, and the thing that we are working on was Converged, BootGuard, and TXT. Basically, they merged both technologies together, right? Both of these technologies are leveraging ACMs, so authenticated code modules. Instead of having a set of ACMs for TXT and a set of ACMs for BootGuard, you have one set of ACMs for both now. Also, they moved the configuration data around a little bit. Before that, you had configuration data in the TPM, and you've had configuration data in the fit tables and these kind of things. Now they moved it basically into one structure, which is called the boot policy manifest, which I will go in more detail on the next slide or so. However, they moved these parts around. They also have another thing called key manifest that I will talk about later, and all the configuration data. So what you need to configure CBNT basically is a couple of fit table entries, a couple of ME configuration, but it's like 3 or 4 things, a key manifest, and a boot policy manifest. So what's a key manifest? A key manifest is a binary structure that lives in your firmware or has to be placed in your firmware. It contains metadata like an SVN, also a security version number. It has an ID, it has a revision, and all these kind of things. But it also contains the hash, or let's say, first of all, key manifest and boot policy manifest are signed structures, right? So they are binary structures, and they have a signature appended to them, which to verify the integrity of that binary structure. The key manifest itself contains the hash of the boot policy signing key, or let's say the public part of the boot policy signing key, and has a hash of its own public key in there and a signature. The boot policy manifest on the other side also again has metadata, and it basically has all the configuration data needed to configure CBNT properly. So it has metadata like ID, SVN, revision, and so, but it also has, which is like the most important thing that you may be looking for, is it has your IBB segments saved in your boot policy manifest. So the boot policy manifest basically defines where your IBBs, your initial boot blocks that you need to define in order to build up your trusted computing base, where they are in the firmware, in the flash. So the IBB segment is basically defining the part of the flash as IBB with the corresponding measurements, so with the corresponding hash values to the IBBs. It also has CBNT configuration parameters like TXT mode, like in what mode do you want to have TXT running, in what mode do you want to have BootGuard running. There are a couple of profiles that you can set for BootGuard and for TXT, and that can all be configured in the boot policy manifest. If we look into the how CBNT builds up its chain of trust, or basically its root of trust, and where the platform then builds up the chain of trust, it's basically all starts with the internal ME, right? They shifted everything into the ME or into the ME fuses, and are using ACMs again to verify the first thing that runs. So if the platform boots up, the ACM loads. The ACM also has a signature, and the CPU itself checks the integrity of the ACM if everything's fine. And if everything is fine, the ACM starts up. Once the ACM is started up, it is looking for the key manifest. It is verifying the integrity of the key manifest by checking the signature of the key manifest and checking if the hash of the public key of the signature of the key manifest is burned into the ME. If that is the case, it continues looking for the boot policy manifest. If it finds the boot policy manifest, it again checks the integrity of the boot policy manifest and then checks if the hash of the public key with which the boot policy manifest has been signed, if that hash is actually in the key manifest. If that is also the case, CBNT knows, okay, you have the right hash of the key manifest in the ME, and you have the right hash from the boot policy manifest in the key manifest. Now I can check your IBBs. You can define multiple IBBs, and it goes through the list of IBBs that you have in your boot policy manifest and gets all the IBBs, measures them all together, and checks if all the hash values are correct. If the hash values are correct, it does start your reset factor of your CPU, and your BIOS can actually take over, right? This is how you set up the trusted computing base with CBNT. So what we did is we developed a suite called the Converged Security Suite, which is an open source suite to enhance provisioning of intersecurity technologies in firmware, and also gives the ability to audit the security settings. It can run a test suite, for example, against legacy TXT, but it can also provision legacy TXT. It's firmware agnostic, meaning that it can run basically on every, or not basically, it can run with every firmware. So it doesn't care if you have UEFI or if you have open source firmware like we do, or if you have anything else. As long as you stick to the specification, everything's fine, right? We just released a new version called 2.6, which also has CBNT provisioning support, which was basically what we're working on in the last 9 months, to integrate that into the tooling. And we also have PCI 0 pre-calculation integrated there. What else is upcoming? We have BootGuard provisioning support. That is ongoing, and we got key manifest validation, and we got boot policy manifest validation. Also, CBNT test suite is incoming right now, so that is ongoing. The thing that we try to solve here with the Converged Security Suite is that everything, as I said initially, everything that we had before was closed source, and that is actually not a good thing, right? If you're running like big infrastructure or just some server or whatsoever, and security matters actually, you're processing private data or whatsoever, you need to know how your platform has been set up. If that is actually not the case, we're getting into trouble here. So that means if you want to have a secure system, you need to know what your firmware is actually doing and how it is configured. And to solve this problem, we developed that Converged security suite, who basically does the job for us. How did we do it, or like what approach did we go? And to be honest, it's pretty much straightforward, right? I would love to make it up more complex, but however, it's pretty much straightforward. All the documents, or there are a couple of documents about CBT, and Intel provides them all under NDA, so you cannot share them freely. However, all the structures that you need to implement, like the key manifest, the boot policy manifest structures, are well documented under NDA. So you can get, if you write tooling for these kind of things, you can basically just copy what's in the specification, put that into Golang code, and off you go. However, there were a couple of things that we had to work around. There was, for example, key generation. As I said, all these structures are signed with a key, and also it was not clear from the beginning what kind of keys do they use. Are they using RSA keys? In what format do the keys need to be? And all these kind of things. That needs to be specified very, very strictly, actually, for these things to work. Also, how the signatures actually been generated is unknown. So the ACM does check the signature of the KM and the BPM, right? However, how it does that and what are the conditions if something goes wrong, that is unclear. So there was a lot of try and error in what parts of the KM and what parts of the BPM need to be signed in order that the ACM is happy, right? Because basically what you're doing is black box testing. You're testing again a binary coming from Intel to make it happy, right? And that was quite tedious work. Most of the biggest problems that we had was the hash calculation. As I said initially, the hash of the KM and also of the KM public signing key and of the BPM public key or public part of the signing key goes in either into the ME or in the KM, right? How that hash is calculated, that was kind of strange. The thing is that was not documented, so that was like weeks of try and error and see if we can find a way, or if we can find out how this is done. They're basically endless, or maybe not endless, but there are a lot of combinations that you can go. And the funny thing is actually that the hash that goes into the ME is calculated differently than the hash that goes into the KM. Even though it builds up that root of trust, they do put different hashes, or they actually calculate them differently. Also, they Intel starts to jiggling around with if it's big endiness or little endiness, right? And all these things get you really confused. Also, in the way of going to CBT and going into a measured launch environment in the end, the firmware platform configuration matters a lot, right? There are a lot of registers that needs to be logged. You have to take care of a lot of things that are really not documented, and also that is just moving forward very, very, very slowly. Once you have all that stuff, so you have your key manifest and boot policy manifest set up, right? You find out all how the keys generated, how the signatures generated, and all these kind of things. If you want to release it to the public, that is sometimes a problem. What we basically did is we did like 2 weeks of research, what is publicly known and what not, and everything what is not publicly known now has the name reserved something. We released it and everything's good. What's the bottom line here? With open source tooling, basically that enables you to audit your firmware stack so that you see, okay, what is going on there. The Converged Security Suite is just one tool set that you can use, and it can only audit and validate a very small part of your firmware. However, that enables you at least to look at these kind of things. How CBNT is set up, how BootGuard is set up, how is TXT set up, is my platform configuration actually valid or not, and these kind of things. So it enables you to audit and validate into firmware security technologies, at least TXT, CBT, and BootGuard. And it also lets you configure it to your needs that you actually have. All right. Most important thing, I didn't mention where to get it. So you can find it on GitHub, obviously GitHub/9elements/converged security suite. You can find the link here in the slides. Also, if you have any questions, feel free to contact me. And now I can show you, if you're interested, how that all looks up. I hope you can see my shell. I do that a little bit bigger. So that's a Converged security suite. So everything is Go basically. So that's good. We have the CBNT provisioning tool, but we also have, let me see. But we also have like the BootGuard provisioning tool that's ongoing right now, but I already have it. We got the PCR0 tool, which is there for PCR0 pre-calculation. We got the TXT provisioning tool, and we got the TXT suite. So what I talked about today is the CBNT provisioning tool. So easy as that, as every Go binary, you can just build it. I made a small demo. Basically, I just put here some files. And you can run the CBNT provisioning tool, and it gives you the ability to generate KMs, to generate BPMs, to generate keys, which is quite crucial, and to read out all the information from a BIOS binary. It doesn't matter if it's UEFI or core boot in this case, in a human readable format, right? So, small demo that I'm not talking, that I'm not lying here. That y3dlmo4.bin is a UEFI binary for an OCP server. And if we put that on, you can see, and I know it's messy. Okay. You can see a lot of fit entries here on top. So fit entries is the firmware interface table, which defines where are microcodes, where is my ACM, where are my key manifests, and where's my boot policy manifest. That's basically the information that are in there. And it can find your boot policy manifest, prints out all data that is in there. As I said, it's over hundreds of configuration data that you can do, DMA protection and these kind of things. However, what I wanted to show you is the IBB entry point here. There you can see where the IBB entry point is, and also what hash values it contains. So these are actually the hash values with different hash algorithms for your IBB. And it has a ton of more configuration data out here. In the end, signature, and we also have key manifest, which has, this is actually the hash of the public key of the BPM that you just saw above, and signature, and so on and so forth. So if you're interested in that, please check it out on GitHub. And yeah, with that, I'm basically done.